chance to visit Moscow. Actually, I've been invited to Moscow. This is my first time here. I had been invited a few times, but somehow I couldn't accept it. But this time it really works out. And this seems to be a very nice season now. So okay, so I will discuss something about format principle. So let me start with the problem. So the problem is about geometry of submanifold in complex manifold. And if you want to kind of stick to algebraic, smooth algebraic parameters. So here's the definition. When you are given two compact complex submanifolds in complex manifolds, and a biholomorphism of their geoms means that it's a biholomorphic map between some small neighborhood. So we are interested in Euclidean neighborhoods. And the question is how to check this when you give two compact complex submanifolds. How to check whether they have biholomorphic neighborhood or not. That was that's the basic question. It's sort of the basic problem in complex geometry. And the normal boundary is important. And so we note by NAX the holomorphic normal boundary of the compact submanifold. And I denote by 0 over A, the 0 section of the normal boundary. Is this okay? By the way,
it's okay.
Is it okay?
Yes.
Yes, I denote by 0 lower A, the 0 section inside the normal boundary. When we regard the normal boundary as a complex number. And then the classical result is that a neighborhood of the submanifold is smoothly diffeomorphic to a neighborhood of the 0 section. This is what's the name? This is cubular neighborhood theorem.
Excuse me?
So in differential topology, this is the problem is sort of completely determined by the normal bundle is isomorphic, then you can say that the diffeomorphic neighborhood, there's diffeomorphism of some Euclidean neighborhood. So in the differential topology, the only invariant is the normal bundle. But here we are interested in biholomorphic equivalence of geoms. So this is not necessarily not enough usually. So we have to look at the higher order neighborhood. So I will define it. If I is the ideal sheaf of the submanifold, then we consider the infinitesimal neighborhood as infinitesimal neighborhood. This is the space equipped with the structure sheaf L plus first power of the ideal. And then the formal neighborhood means the collection of all these finite order neighborhood. That's formal neighborhood. And then a formal isomorphism of the formal neighborhood means the collection of isomorphism of this finite infinitesimal neighborhood for all order such that they are compatible with each other under the obvious restriction map. So that is a notion of formal isomorphism. And the existence of isomorphism of the first infinitesimal neighborhood is more or less equal to the isomorphism of the normal bundle. And then the problem of lifting the first order isomorphism, the Lth order isomorphism to L plus first order isomorphism. This is an algebraic question, is a cohomological question. The obstruction to the lifting is in some cohomology group of some symmetric power of conormal bundle. So this is a completely algebraic problem. So consequently, whether you can find the formal isomorphism between formal neighborhood of the submanifold, this is a completely algebraic or cohomological question. So the question you are interested in, so these are sort of well understood. The nature of this problem is well understood. It's a cohomological problem. But the problem you are interested in is what happens. Suppose you, after you get a formal isomorphism, then can you say that there's a isomorphic, biholomorphic neighborhood, the isomorphism of germs? So that's the question you are interested in. So this is formulated in the following way, the formal principle. So this is the main concept we'll consider. So we say that the formal principle holds for compact submanifold in a complex manifold, or the compact submanifold A in X satisfies the formal principle if the following is true. If for any other compact submanifold A tilde in some complex manifold X tilde equipped with the formal isomorphism, and any given positive integer L, there exists a biholomorphism of germs which agrees with the given formal isomorphism up to Lth order. If this can be done for any positive integer L, then we say that formal principle holds. So in other words, this formal principle is exactly the asking the problem that once after you obtain formal isomorphism, whether you can say that you can lift it to a biholomorphic isomorphism. So that is the question. I want to holomorphic in a neighborhood.
Sometimes it's true. Sometimes the stronger thing is true. Sometimes it can recover like normal.
That's right. Yeah. But quite often, once you obtain isomorphism of biholomorphism between neighborhood, very often you can lift it to algebraic, or at least to étale. Yeah. So usually the.
And this question isn't just the question of convergence of the series?
No. Because here you see, we do not formulate it as a convergence, but it's an approximation theorem. Because even in the case of just a point, so suppose you have X with point A, with point, then you can always find formal isomorphism which doesn't converge. So what we ask is, suppose you are given a formal isomorphism, whether you can approximate it by phi up to order L. So this depends on L. So whether you can find the convergent isomorphism which agree with the given formal isomorphism up to L. That is the natural condition. Because asking for convergence is too strong. It's usually not true. So this is an approximation theorem. Okay. And because you have the case of normal bundle is important, so we formulate the vector bundles also. So when you are given a vector bundle W on a compact complex manifold, we say that the formal principle holds for the vector bundle, or the vector bundle satisfies the formal principle. If the zero section satisfies the formal principle as a submanifold of the complex manifold, the vector bundle as a complex manifold. So this is a special case of the previous definition. when you apply it to the zero section of the vector bundle. But there is no direct implication between the formal principle for submanifold in a complex manifold and the formal principle for the normal bundle.
Unless the M is a mode.
Okay, yeah. But in general, there's no, suppose A satisfies the formal principle in X. It does not necessarily mean that the vector bundle satisfies formal principle. And the other way also is not immediate. So there's no direct relation between these two formal principles. Now there are a few cases where the formal principle is known. So the first result was Grauet's, the famous paper on exceptional sets. So if the submanifold can be contracted to a point, then the formal principle holds. So actually, this is the sort of origin of the problem. In proving, in constructing the contraction, the condition for the contraction of a submanifold, Grauet realized that one has to consider this first, one prove the formal existence of contraction, and then he realized that one has to worry about how to show it is convergent. So that's the origin of the problem, sort of. So in the case where the submanifold can be contracted to a point, the formal principle holds. That's what he showed, Grauet showed. Yeah, holomorphically contracted. Everything here is holomorphic. I think he discovered that the condition is formal is enough. So the condition is if formally contractible, then it's holomorphically contractible. That's what he showed, essentially. And then there's a case of flat neighborhood. This is Hirschowitz. So when A is a fiber of a flat morphism, so a smooth morphism, so in particular the normal boundary is trivial. In this case, Hirschowitz showed that the formal principle holds. And then there's a positive neighborhood case. That's Commiscio and Grauet. They proved that if the normal boundary is ample and globally generated, then the formal principle holds. And almost at the same time, Hirschowitz obtained a slightly different condition in the positive neighborhood. So what he showed was that if deformation of A in X having non-empty intersection cover neighborhood of A, then formal principle holds. So this is a more geometric condition instead of Commiscio and Grauet's condition. So this is sort of a geometric version of positive neighborhood. So, but they are different. For example, if you consider this vector bundle, tangent bundle of projective space twisted by -1, this is not ample vector bundle, but it's globally generated. And the Hirschowitz result applies here, but not Commiscio and Grauet. So these two are sort of very close, but somewhat different results. So there are cases like a negative case, flat case, and positive case, the formal principle holds. But the difficulty of the problem is, even if you know, for example, when you know that a vector bundle V1, V2 satisfy formal principle. Does the direct sum satisfy formal principle? This is unknown. And this, there's no way to deduce this. So the problem is no counterexample, but the nature of the problem is very strange. It's not really very linear. It's very non-linear problem. So even if you know.
Can you explain what you mean by deformations and
okay.
So the base should be
So you have the problem is you have manifold X, and you have a submanifold A. And the condition says that if you deform the manifold with some point fixed, like this way you can cover an open neighborhood. That is the... Yes, yes. But the map has to be restricted to those submanifolds which intersect this A. This is very technical condition. But for some cases you can check, but it's very so because of this, the problem is very nonlinear. For example, even for homogeneous vector bundles on projective space, it's not completely understood. Which homogeneous vector bundle on projective space satisfy formal principle? This is still not understood. So it's a very nonlinear problem. And then there's a counterexample. So there's Russian now in this talk, at least. Arnold discovered a line bundle of degree 0 on an elliptic curve, which does not satisfy formal principle. And this construction is modeled on the divergence of Poincare normal form on holomorphic vector fields. The problem in celestial mechanics. So this small denominator problem. In particular, there are two germs of holomorphic vector fields in C2 in a neighborhood of 0, such that you have formal isomorphism sending one vector field to the other, but there's no biholomorphic isomorphism sending the vector field to the other. So this is because the denominator becomes too big, the formal solution, so it doesn't converge. You cannot find any convergent solution. So using this example, Arnold sort of modified this example in the setting of elliptic curve, neighborhood of elliptic, and produced this counterexample to formal principle. So the problem is very delicate. Even in the case of surface, a curve in a surface, the problem is not easy. Now let me briefly overview the proof of this known result. How to prove this kind of result. So this is essentially, you can say that everything is reducing the problem to Artin approximation theorem. So Artin approximation theorem is the following, that if you are given any finite collection of analytic equations for finitely many unknown functions in, say, n variables in a neighborhood of the origin, if there's a formal solution of this analytic equation, then to any given order, you can find a convergent solution which approximate the given formal solution. So this is a general, very general approximation theorem. So essentially, any analytic equation, if it has a formal solution, it has a holomorphic solution locally. That is the result. The problem is that this is a local result. So this works only for germ of one point. The problem we are interested in is germ of some positive dimensional neighborhood. This works applies to only a germ of a point. So that is the problem, that you cannot generalize this to neighborhood of positive dimensional submanifold. So the proofs of formal principle in the known cases involve certain localizing procedure where they localize the problem to a neighborhood of one point so that one can apply this Artin approximation theorem. That is the general approach of the known cases. So here's the one-point localization. So suppose the submanifold can be contracted to a point, then you can localize the problem to the contracted point. So the problem is concentrated on this one point on some complex space. So I may be singular, but Artin theorem works for singular case also. And when A is a fiber of a flat morphism over base point, then the problem is localized to the neighborhood of that base point. So again, you reduce it to 1 point somehow. Now what happens to positive neighborhood case is that all the known results, Grauet, Commiscio, Hirschowitz, they actually prove the convergence of the power series, the formal series. So in the case of positive neighborhood, it's not an approximation theorem, but convergence theorem. And then when you are interested in convergence of a given formal series, it's already a local problem at each point. You are supposed to prove the convergence at each point. So at each point, it is localized. So the problem is localized to neighborhood of each point, essentially. So all of them involve some localization procedure to 1 point, and then apply Artin approximation theorem. Now it's interesting to observe the role of global generation of the normal bundle. So in the known cases of the formal principle, at least in the semi-positive neighborhood case, the normal bundle should be globally generated to have the known result. So in the case of flat neighborhood, the normal bundle is topologically trivial, and then the formal principle holds if it is globally generated. This is the case of Hirschowitz. On the other hand, we know that analytic example is the formal principle does not hold, and in this case, the normal bundle is not globally generated. So somehow the distinction between Hirschowitz result and Arnold's counterexample has to do with the global generation of the normal bundle. And then also Commiscio and Grauet and Hirschowitz, all the results require global generation of the normal bundle. And it is still not known whether the formal principle holds when the normal bundle is only ample but not globally generated. Then it's not known. So it seems that global generation is a key property here. So this motivated Hirschowitz make the following conjecture. So if the submanifold is unobstructed and the normal bundle is globally generated, then the formal principle holds. So unobstructed here means that any section of the normal bundle can be realized as deformation, the initial velocity of the deformation. And equivalently, this conjecture says that the formal principle holds if the duality space, or Hilbert scheme in the algebraic setting, if the duality space is smooth at that point corresponding to the submanifold, and the universal family map is submersive near A, near the submanifold, then the formal principle holds. So this is the conjecture. In particular, this conjecture predicts that a globally generated vector bundle on a compact complex manifold satisfies the formal principle. And in fact, Hirschowitz's original version of the conjecture was more general and somewhat complicated because he doesn't assume the submanifold is unobstructed. But so I formulated here slightly simplified version of his conjecture, assuming that A is unobstructed. Okay, so that is the conjecture. And what is the difficulty of this problem? The difficulty is, as I already said, the known methods of the formal principle in the positive neighborhood case prove the convergence. On the other hand, the flat neighborhood case, the problem, you cannot expect convergence. It's an approximation theorem. And the conjecture somehow asks to combine these two, the positive neighborhood and the flat neighborhood. One has to combine these two results. But because of this nonlinear nature of the problem, knowing the problem for positive neighborhood and knowing it for flat neighborhood does not guarantee why you can do it when it's combined. So this is sort of, the question is how to combine two different results like this. So it's a version of this kind of question. What Hirschowitz formulated is a version of to what extent you can combine two formal principles together. And the difficulty is that the nature is very different. The nature of the method was very different. In the positive case, it's convergence. In the flat case, it's just approximation. So it's very difficult to combine these two fundamentally different approaches. So that was the difficulty. Okay. So let me now state my main result. The main theorem is slightly complicated. So I consider a connected open subset in the duality space, and such that for each member of this open subset, for each member of this open subset, the submanifold is unobstructed with globally generated normal bundle. And I also assume that global sections separate points. So this is the additional condition I need. It's not just globally generated, but it separates points in this sense that sections vanishing at two different points are different. Then I say that the result says that then there exists a nowhere dense subset of this open set such that any member belonging to the complement of this nowhere dense subset satisfies the formal principle. So in other words, the result says that if we assume that the normal bundle is globally generated and separate points, then Hirschowitz conjecture holds for sufficiently general A. So it's not exactly all A, but you need to exclude some special subset. So once you have a manifold with a globally generated normal bundle and separating normal bundle, which separates the points, then you can deform the manifold and you can say that the formal principle holds. So if you like to see more explicit example, the original motivation of the problem was cases like this. So I mean, people are interested in cubic hypersurface nowadays. So suppose you have a cubic hypersurface. And suppose you choose a line. And the question is whether this line satisfies the formal principle. And this is unknown still. But this result says that if the line is sufficiently general, then it holds.
This is probably proof of cubic surfaces.
Cubic surface is known, okay. But I'm talking about at least dimension 4. Cubic threefold is also known because trivial neighborhood. The neighborhood is trivial. I'm smooth. Yeah, for general line bundle, I mean. General line, or at least free line when the normal bundle is generated. But if you go to higher dimension, this is still unknown. That whether free line satisfies the formal principle is unknown. But my result says that at least sufficiently general line satisfies the formal principle. O1 all the way except 2O. Yes. So this was actually the original motivation because I studied this kind of problem, and actually Ozawa asked me whether this is true, and I didn't know this problem, the Hirschowitz conjecture, until he told me that there was such conjecture, and I realized that this is a problem to. Yes, yes. I think he started as a more complex analyst. I think he was a student of Duadi. Yeah. Okay, so this is the result. And the result is slightly technical, but there are several corollaries. So the first corollary is that if W is a globally generated vector bundle on a compact complex manifold, and if the sections separate points, then the vector bundle satisfies the formal principle. And this is because our main theorem, what I just stated, says that sufficiently general deformation satisfies the formal principle. So for sufficiently general section, it satisfies the formal principle. But for vector bundle, any section have an isomorphic neighborhood. So if the result holds for, if the result holds for sufficiently general section, then it also holds for zero section. So vector bundle, if it separates, if the section separates points, then the formal principle holds. And then there's a corollary. Another corollary is that if the vector bundle is globally generated on a Fano manifold, then it satisfies the formal principle. So on a Fano manifold, we don't have to assume it separates points. It's just globally generated enough. So this proves the Hirschowitz conjecture on Fano manifold. And why we don't need global separation of points? Because you can add anti-canonical bundle, sufficiently high anti-canonical bundle, then the total vector bundle, the sum of these two vector bundles as global sections separates in points, because this anti-canonical bundle part separates already the points. So then you can apply the previous corollary to this, and because of the nature of the problem, in the formal principle, after you prove it for the sum of the vector bundles, you can eliminate one part on Fano manifold. It's a nature of the sign is in such a way you can eliminate the other part. For example, you cannot do this when it is canonically polarized. Then you would say, why not just add some power of canonical bundle? In that case, after you prove formal principle for the sum, you cannot separate out W from this. The sign is somehow twisted. So only for Fano manifold you can use this trick. But anyway, for Fano manifold now you can prove it. And then, as I say here, is any sufficiently general smooth free rational curve satisfies the formal principle. You don't need any Fano. Any complex manifold. Because if it deforms, some sufficient general one always satisfies this. So because this is, if the normal bundle is trivial, then this follows from Hirschowitz result, the flat case. And if the normal bundle is non-trivial, then global section separates points always on P1. So especially this case. You can. Now if the normal bundle is ample, if the normal bundle is ample, then this already is covered by Komisho-Grauet or Hirschowitz, because the deformations intersecting the curve sort of cover an open neighborhood. So the really interesting case of this result is when it is not, the normal bundle is not ample, but only free. So especially the minimal rational curves, when the rational curve is very small degree. This is the case mostly interesting in our setting. Okay, so that's the corollary. Okay, now I'll explain in the remaining, I don't know how much I have, maybe 20 minutes. Okay, I have enough time, okay. So I'll explain the proof of main theorem. And this proof also we have to localize to one point. Now how do you localize to one point? So now I need to illustrate this. So we are in the main theorem, we are considering complex manifold X and some open set in the duality space. And then we have the universal family. So here's a universal family, and there's a morphism U. Such that our given A is a fiber here. So we have this duality space. So this is inside duality. So you have this kind of universal family. And what we do is we localize at a point, a general point on the universal family, a point like here. So we look at this point. So this is something slightly different from the older approach. The older approach, people only look at point on the manifold. Now we look at the point on the universal family of duality space. Now the fiber in this direction has a flat neighborhood. On the other hand, the fiber on this direction, this accounts for the positivity of this neighborhood. So this fiber exactly shows the deformation of A fixing that point. So by going to this point on the universal cover, you combine the flat and the positive neighborhood somehow together. So this is how you combine these two different arguments, the flat case and the positive case. Okay, so by going to a point here, you combine these two cases simultaneously. Now, how do you actually make this? So let me see. Let's start with the, this is maybe too big. So let me draw slightly smaller scale. So let's look at the problem. The problem is you are given two manifold X and X tilde, and two submanifold A and A tilde. And then we have corresponding universal family U, K, and so you have these two duality, universal family of duality spaces. And now we assume that there's a formal isomorphism from A to A tilde. So this is formal. In a formal neighborhood, we have isomorphism, formal isomorphism. Now this is already observed by Hirschowitz, that the duality is a functor. So because of this functor, you can apply it to a formal neighborhood. So this formal isomorphism lifts to a formal isomorphism on A. So if you look at a point here, it lifts to a formal isomorphism. This is because duality is a functor. So in particular, the formal neighborhood of duality space is the duality space of the formal neighborhood. So they commute. So any given formal isomorphism can be lifted to a formal isomorphism of the duality space at the universal cover in such a way this formally preserves the double vibration. this double fibration, and so this phi tilde preserves double fibration in the formal sense. So these two spaces are equipped with double fibrations, and this formal isomorphism preserves this double fibration in a formal infinitesimally. So that is the setting. And then the key point here is that the key claim is that this formal isomorphism can be approximated by biholomorphic isomorphism outside the nowhere dense set. So this formal isomorphism on the universal family can be approximated by biholomorphic germs of this point, which preserve the double fibration. That is the main point. So the Artin approximation says that any formal isomorphism of point, of course, can be approximated by biholomorphic isomorphism. But here we are requiring something more. We are requiring, this is the key property. We require that this biholomorphic map preserve the double fibration. So this is the extra information we hope. This is not just approximation of the formal isomorphism, but it's an approximation which preserves the double fibration. That is what we want. And this is the main point, that the key claim of the proof. Now, once you have this key claim, then once you obtain a biholomorphic map between, so once this becomes biholomorphic, then and which preserve the double fibration, then you can now analytically continue this in a neighborhood. That's the argument, because this the point is that this analytic continuation of biholomorphic map preserving the double fibration along these fibers, it may become multi-valued, but exactly the requirement that the global sections of the normal bundle separate points is somehow guarantees that this is single valued. So you can extend it in a neighborhood here of double fibration preserving maps of the neighborhood. And then this map can be descended. Because it preserves the double fibration, it can be descended to obtain the map you want. And this kind of analytic continuation is what I used with, in my work with Moog long time ago. So it's a sort of inspired by that analytic continuation argument. So the main point is just approximating it. The key, so this says that the key claim implies the proof, essentially. So the main point is how to prove the key claim. So the key claim is when you are given so key claim has nothing to do with the, in a sense, with the duality space. It's just this, that you are given a manifold U and manifold U tilde. And you have a double fibration here. And double fibration here. So this, you have two manifolds with double fibration, or two foliations. You have two manifolds, each has two foliations. And you are given a formal isomorphism of a point in the neighborhood of point, preserving double fibrations. And the question is, can you approximate phi by convergent isomorphism, preserving double fibration? So this is a real problem. The problem is this duality space problem is now completely reduced to this problem about manifold with double fibrations. And formal maps preserving the double fibration, whether you can approximate it at a given point in a neighborhood of a given, it's localized already, just one point. Whether you can approximate it in a neighborhood by convergent isomorphism, that is the problem. But we have to preserve the double fibration, that is the difference. So the problem looks like Athena approximation theorem. So to prove the key claim, you have to solve a differential equation. The condition of preserving double fibration is not an algebraic or analytic equation. It is a differential equation. So that's the difference. So one hopes to have this kind of Athena approximation for PDEs. So you are given a finite collection of analytic PDEs. So this double fibration is a kind of PDE. So you are given a finite collection of analytic PDEs in n variables. And suppose you have a formal solution of the PDE. Can you approximate it to any given order by convergent solution? So this is the, if this is possible, the answer is we can solve this problem. Now, unfortunately, this is not true. This Athena approximation for PDE does not hold. Because exactly as we saw, there are cases like divergence cases of Poincare normal forms, where there's a system of analytic PDEs, the isomorphism of two vector fields, the conjugation of two vector fields we mentioned, this is exactly an analytic PDE, and which has a formal solution, but which does not have local holomorphic solution. So you cannot, this result is not true. So you cannot apply this kind of result. So that's the difference between Athena approximation and our setting, is that we need to solve a differential equation. Athena is just an algebraic or analytic equation. There's no derivative involved in Athena case. But in this problem, we have to solve a differential equation. So that is the... Yes. Holomorphic solution means it's a solution to all order. But here we want to approximate the given formal solution. So the solution we want is a solution to all order, but it agrees with the given formal solution up to a given order. So this is approximation theorem.
But what I'm saying is that not being true of the second statement does not imply the first theorem.
This one, system of analytic formal solution is the local. Well, this implies, because if the theorem is true, then if you are given a system of analytic equation, PD, with a formal solution, there must be a holomorphic solution also. No. If this hypothetical theorem is true, this hypothetical theorem claims that if the PDE has a formal solution, then first of all, there exists a holomorphic solution. And moreover, the holomorphic solution approximates the given formal solution. That is the claim. But just just the easy consequence, this already is violated. There's a situation where there's no holomorphic solution at all, whether approximating or not. So this cannot be true. Now, luckily, there's a result in this line. This is Malgrang's sort of approximation. This is called the refined Cartan-Keller theorem. It says that if it's not true for any system of analytic PDE, but if the system is involutive, so this will be explained soon, but there's a certain system of PDEs which are called the involutive system. For involutive system of PDEs, this is true. that if the system has a formal solution, then there's a convergent solution approximating the given solution, formal solution up to any given order. So it's miraculously the previous version is not true. But if you assume that the system of PD is involutive, this condition, then it's true. So now what is the involutive? So involutiveness of a system of PD, this is an algebraic property of the system of PD. And the system of PD corresponds to certain subscheme in Z spaces of the manifold. And this involutiveness means that some morphism on this Z scheme, subscheme of Z space is smooth or reduced. So that's a kind of condition. And this, this is really analytic result. So this is sort of our essential analytic result. This involves, uses Grauet's privileged neighborhood theory. Now the problem is how to check this involutiveness. This is the technique. You just pushes the problem into something else, involutiveness. Because this condition is extremely complicated. If you look at books on system of PDEs, the involutiveness is usually explained in at the beginning I couldn't understand what they mean. It's an extremely complicated way. The reason is that they don't understand, they don't use the language of algebraic geometry. I think that's the problem. If they state things in algebraic geometry language, it becomes much more clear. But they usually state the smoothness of subscheme by counting certain dimensions. Essentially, they like to say that the certain part of the subscheme is complete local complete intersection. But they express this in terms of PDE. So it's very complicated. Anyway, the checking the involutiveness is usually very hard. And our setting is very general. So how to show this? So there was a big problem. But again, very luckily, there was a Cartan's procedure. So Elia Cartan, more than 100 years ago, he claimed the following. So it's a kind of without proof. He claimed that any system of PD becomes involutive if you look at the sufficiently general point. So if you exclude some special set, then it can be made involutive after prolongation. The prolongation means that when you are given system of PD, you take derivatives and add more equations. So what he says is that if you sufficiently add more and more equations, and if you look at sufficiently general point, then it's okay. It becomes involutive. And this is just a claim or just a prediction. And but many people worked it out rigorously, so in many settings. And in particular, for our purpose, for systems of PDs describing equivalence like this, equivalence of G structures. So when double fibration is a special case of G structure, and for equations describing equivalence of such structures, Morimoto worked out this rigorously. And first, when the structure is transitive, when the group is the same at every point, this was done by Singer and Sternberg, and Morimoto generalized it to arbitrary case. So we have very luckily this result of Morimoto exactly proving the involutiveness of this equation at a sufficiently general point. Prolongation is required. You have to, yeah, just the equation describing the equivalence is not enough. You have to take all the derivatives of this equation and add more and more. That's why we need to exclude some nowhere dense subset. So at some points, after taking derivative, you exclude one. And then to add more derivative, you have to exclude some more and so on. So these are. This subset is unfortunately right now it's not explicit. It's supposed to be closed subset, but they do not prove this closed. It's just nowhere dense.
So it is taking higher correlation, just going higher expectation.
Yes, yes. But you have to go, you have to add more equations by coming from here. And so the main result in that setting is there's a stabilization theory. That this process stabilizes. This was a result of Kuranishi and those people. They show that this stabilizes. So now you can use the Morimoto's theorem. The system of PDs describing the analytic equivalence of holomorphic G structure like this. It becomes involutive if you exclude some nowhere dense subset. Yes. So now you can apply this to our setting. So you can use the Malgrange-Cartan-Keller theorem to find such approximation. So that's the end of the proof. Thank you. This one. This one? This one? Oh, this is actual result.
Yeah.
No. Up to a given L. For each L, you can find some holomorphic solution which agrees with the formal solution up to that order.
Okay, so statement in the second line means holomorphic solution that holds for all orders.
Okay, maybe I'd better just to avoid the confusion. This is pseudo theorem. This is pseudo theorem. Claims that if there is a formal solution, formal solution, whatever, PC, then there is holomorphic solution. This pseudo theorem claims this first, and then there's extra property. But this counterexample does not even have any holomorphic solution at all, so it certainly cannot be true. Okay. How general is I think there's a generalization of Arnold's example by Arnold's students.
No, but say, anyway, just 2 points on elliptical, right?
2 points on elliptical.
What degree 0 or 1 point? So there is a 0 and then some other point.
Yeah.
So general point.
There's for line bundle on elliptic curve. This is the Picard group is elliptic curve.
Elliptical, right?
So there's an arithmetic condition with respect to the torsion. So this line bundle is not torsion line bundle, but sort of very close to torsion in some way. Okay. Yeah. So there's some Diophantine condition. This is the same in this small denominator problem. There's always some Diophantine condition between the eigenvalues, which makes the things divergent.
So it might be expected to be like a very, very general.
Yeah, there are some work later where there's more, they analyze this neighborhood elliptic curve very much. I mean, Japanese mathematicians like Ueda, they analyze this. So there's lots of theory there. Yeah. Geometry application, okay. Originally, I don't know whether you know this, but long time ago, what I proved with Moog is if you have, for example, cubic threefold. If you have a cubic threefold with two lines whose neighborhood are biholomorphic, then we show that x and x tilde are biholomorphic. When the dimension is 4. Now the problem with this has some application, but the problem with is limited because you have to check the isomorphism in the neighborhood, and this is not in general it's not algebraic condition. So I want to make this more algebraic, and this is sort of the first step. That instead of biholomorphic neighborhood, it's enough to check formal neighborhood. Eventually, I hope to replace it to some finite neighborhood plus some other condition. The more algebraic condition. That's
How big is the gap between holomorphic and random, for example,
for vector bundle, holomorphic and
so you have then how far is it like a vowel?
for vector, that's a good question. I never considered the vector bundle case, but like for Fano or Picard number 1, biholomorphic means biregular.
Yeah, the same.
So because you can analytically continue the map. So for vector bundles, I haven't considered this.